Okay, hello everyone. In this screencast, I'm going to show you how to do some example problems involving calculating voltage for point charges. The primary equation that we're working with here is the one up on the screen. It reads V is equal to KQ over R. Now, in this equation, okay, if we look at this value here, that's the voltage. Whereas the K value here, that is Coulomb's constant, which if you remember from our previous unit, has a value of 9 times 10 to the ninth power with units of newtons times meters squared per coulomb squared. Q represents the charge that we're dealing with in coulombs, and the R value is just the distance of the center of the charge to the location to where we're trying to calculate the voltage. Okay, so let's jump in and try a practice problem. What I have here is a positive charge, and I'm interested in calculating the voltage some distance away, 0.3 meters to be exact. So we're going to call the location that we're interested in calculating the voltage point P. Alright, in order to do this problem, I do need to know the value of this grouping of positive charge. So I'm going to assign it a value of 2 microcoulombs. Now, this symbol here is the Greek letter mu, and we use that in metric notation to indicate micro, which is 1/1,000,000th. Alright, so we'll need to convert that when we solve for the voltage. So let's get to it. Voltage is equal to K, Q over R. In terms of my substitution, alright, the K value is my Coulomb constant. It has a value of 9 times 10 to the ninth, that's 9 billion. And the units here are Newton times meter squared per Coulomb squared. The value of my charge Q is 2 microcoulombs. In order for my equation to return a correct value, I do need to represent that number in coulombs, which means I need to convert. So 2 times 10 to the negative 6th power coulombs is equivalent to 2 microcoulombs. And that I'm going to take and I'm going to divide that out by the distance to point P, which is 0.3 meters. And since the distance is already given in meters, there's no need to do that conversion. And then I'm going to take and put all this into my calculator, and if you do it correctly, and you should definitely try this, you're going to get a value of 60,000. And since we are calculating voltage, the unit is the volt, which gets abbreviated with a letter V. Okay, so now how do we deal with groupings of charges? Alright, unlike the previous problem where there was only one positive charge, I've added in a second one. If you look closely here, you'll see that I've kept the 2 microcoulomb charge from the previous problem, but now I've added in a second positive charge with a value of 1 microcoulomb over here on the right. I'm interested in calculating the voltage at some point in space that we're calling point P. I've also kept the distance to point P from this charge over here at 0.3 meters. And I've also placed the 1 microcoulomb charge 0.3 meters away from this point in space that we're calling P. Notice that the two charges are actually the sum of those distances, are 0.3 plus 0.3 is equal to 0.6 meters. So the two charges are 0.6 meters apart, and I'm looking for the voltage right in between them. Alright, to make this easy on myself, alright, I'm going to take and I'm going to call this charge over here on the left charge 1, and I'm going to call this one over here on the right charge 2. If we think back to the first problem, the contribution from charge number 1 is still going to be 60,000 volts. Same location, same charge, same voltage contribution. In order to get the total voltage at point P, though, I need to know the contribution to the voltage coming from charge 2. So I'm going to write my equation for voltage from point charge, KQ over R, and now I'm talking about the contribution from charge 2 at location from charge 2. K is Coulomb's constant, 9 times 10 to the ninth. Charge 2 has a value of 1 microcoulomb. And remember again, I need to plug this into the formula in coulombs. And so I need to convert micro into standard coulombs by multiplying by 10 to the negative 6th. And I divide by the distance of 0.3 meters. And again, meters are 0.3 is already in meters, so there's no need to convert. So the voltage from charge number 2, if you calculate this out, is 30,000 volts. To calculate the total voltage at point P, All I need to do is take the individual contributions to the voltage coming from charge 1, and add it to the voltage coming from charge 2, and I'll have my answer. Voltage 1, 60,000 volts. Voltage 2, 30,000 volts. And so the total voltage at point P is 90,000 volts. See how easy that is? That's why we like voltages. They add as scalars. Okay, so now how do we deal with negative charges? Very similar problem to the previous one we worked. I've still got my 2 microcoulomb charge. I'm still looking at calculating the voltage at point P, which is 0.3 meters from my 2 microcoulomb charge. But now 0.3 meters away from point P, I've now thrown in this negative charge. Let's keep the 1 microcoulomb value from the previous problem, but because we've got a negative charge here, we've got to account for that. Remember, charges come in 2 varieties, positive and negative. If it makes it easier, I can put a positive value over here just to further distinguish. As far as my approach to solving the problem, all right, I'm going to follow the same basic method where I'm going to call this charge 1. I'm going to call this charge 2. Now, yet again, the voltage coming from charge 1 is still going to be that same 60,000 volts. But what about the voltage coming from charge 2? I'll show you the calculation again, KQ2 over R2. And if you're clever, you can probably skip the substitution here because the K value is the same. The magnitude of the charge is the same, but the sign is the opposite. So 1 times 10 to the negative 6th would be my charge value in coulombs, and it's the same distance of 0.3 meters. In terms of my calculation, everything going in my calculator is exactly the same except for that negative sign. And so the voltage induced at point P from charge 2 is now negative 30,000 volts. And the overall effect on that is if I calculate the total voltage at point P, I'm still just taking the 2 individual voltages and adding them together. All right, but now I've got a contribution of positive 60,000 volts from the positive charge and negative 30,000 volts from the negative charge. And so really, I'm just subtracting 60,000 minus 30,000 gets you 30,000 volts. Not too bad. Okay, so here's a problem for you to try. I have 2 new charges with 2 different magnitudes for their charge, one 3 microcoulomb, one negative 5 microcoulomb. And I've also changed the location that I'm interested in finding the voltage. So my new point P is here, and I've got the distance from the positive charge and the negative charge here for you. I will tell you the answer to the problem, but I'm not going to show you the work. You really do need to try this on your own, and these are problems that you're going to need to be able to solve. So this would be a good point to stop this video and try the calculation, and then come back a little bit later for the answer. I know you want to know the numerical value, so let me give it to you. It is negative 157,500 volts. Good luck to you. See you next time.